Mind-blowing science behind James Webb Space Telescope's 18 golden honeycomb mirrors. The world's excitement for the James Webb Space Telescope launch is touching new heights. A $10 billion mission, the James Webb Space Telescope will be the largest, most powerful, and most complex space telescope ever built and launched into space. Webb will take us on a journey that will help us look back in time, revealing how our universe looked just 100 to 250 million years after the Big Bang, and will eventually help us understand the formation of the first ever galaxies. But some question arise when we talk about James Webb, like what actually James Mirror is. Why is it gold? Why exactly 18 hexagonal mirrors? How deep will James Webb look? All these questions answer you will get in this video. In simple words, the James Webb Space Telescope, named after James Edwin Webb, will redefine our current understanding of the colossal cosmos. The James Webb Space Telescope is nothing less than a marvel of humanity's innovation. However, what differentiates Webb from all the space telescopes launched so far is its unique mirror system. The composition, geometry, and arrangement of Webb's mirrors make them one of a kind. Most of us must have heard that Webb's primary mirror comprises 18 closely packed hexagonal mirror segments. But there's a lot more to it. The fabrication of mirrors. For any telescope out there, the primary mirror is like its heart. The primary mirror is the one that captures all the light, which is further processed to produce the dazzling images of the cosmic wonders beyond us. This makes the fabrication of the primary mirror one of the most intricate tasks in developing a telescope. Many factors need to be taken into account while fabricating a mirror. For example, the mirror must be lightweight yet extremely sturdy enough to withstand the launch exertion and other physical pressures. So to realize these properties in Webb's mirrors, the usage of beryllium was taken into account. Beryllium is a light metal that is very strong for its weight. It is a good conductor of electricity and heat, and is not magnetic. Moreover, it is extremely good at holding its shape across a range of temperatures. All of this made beryllium is a desirable choice for manufacturing Webb's primary mirror. To construct the mirror, a finely powered class of beryllium-030 was used. The mirror segments were first brought to life at beryllium mines in Utah and were later moved across the USA for processing and polishing. In total, the primary mirror is composed of 18 hexagonal-shaped mirror segments, with each one of them being 1.32 meters in diameter and weighing approximately 20 kilograms. In addition to this, the convex secondary mirror is about 0.74 meters in diameter. Each of the telescope's mirrors has been carefully covered in an extremely uniform and microscopically thin layer of gold. The gold coating optimizes the segments specifically for reflecting infrared light, which is the primary wavelength in which the James Webb Space Telescope will decode the cosmos. Why is it gold? Aside from its hexagonal shape and enormous size, Webb's most distinctive feature is the shiny, bright gold color of its mirror. It had such a striking appearance that NASA even held an art challenge open to public submissions of art inspired by the space telescope. So, why gold? Feinberg said, "For one, it is extremely reflective, which is readily apparent in its brilliant appearance. It has this amazing reflectivity. Gold actually has the highest reflectivity over a very wide wavelength band. The reason you build such a large telescope is to catch every individual photon," he added. "So you also want the reflectivity of each of these coatings to be extremely high, so we don't lose photons along the way." Webb's mirrors are said to be 98% reflective, meaning they reflect 98% of incoming photons, which is about as reflective as it comes. Feinberg added that it's also a protective gold that has an overcoat. It's a very rugged coating. Now, while Webb's mirror segments are coated in gold, they are not made of solid gold. They are actually constructed from beryllium, a strong but lightweight metal. Each mirror piece weighs about 46 pounds, which is 20 kilograms on Earth. In addition to being extremely durable, while comparably lightweight, beryllium can also hold its shape at the extreme cold temperatures that Webb will need to operate at, according to the NASA statement. Why exactly 18 hexagonal mirrors? The power of a telescope directly depends upon how big its primary mirror is. The larger the primary mirror, the greater the amount of light collected from the distant objects, and the better the observations. Looking at JWST's bucket list of future observations, it needed a monstrous primary mirror. But there was a problem. Such a mirror could not fit inside any of the existing rockets as one single large mirror. So what now? This was when the team came up with a revolutionary idea to dissociate the primary mirror into 18 small segments that can fold to fit inside the rocket fairing. Now you might wonder why they chose to go with hexagonal geometry and not a square, triangle, or other shapes. There's a logic behind it. A roughly circular overall mirror shape is desired to focus the light into the most compact region on the detectors. Any other geometry doesn't give the required results. For example, an oval mirror produces elongated images in one direction, while a square mirror sends a lot of the light out of the central region. So overall, an approximately circular shape was needed to make the most of the James Webb Space Telescope. The hexagonal shape has a six-fold symmetry that gives it a high filling factor, which further aids the segments to fit together without a gap. So a honeycomb-like pattern allows each mirror to perfectly fit together with the least amount of dead space in between each other. This effectively creates a singular and massively powerful unit, which also makes the desired approximately circular shape of the primary mirror. Managing the 18 mirror segments. Okay, so now we have 18 mirror segments with us, but how to align and focus them perfectly as a single flawless mirror? This is where actuators come to work. Actuators are tiny mechanical motors that beautifully aid in achieving a single perfect focus. In the case of the James Webb Space Telescope, the primary mirror segments and the secondary mirror are moved by 6 actuators attached to each mirror piece's back. Moreover, the primary mirror segments also have an additional actuator at their center that helps in adjusting their curvature. All the actuators have been designed to make adjustments precisely without disturbing the other segments, which will further allow Webb's mirrors and other instruments to work in perfect coordination to create compelling and error-free observations. Speaking about the fine engineering involved in the construction of Webb's mirrors, Lee Feinberg, who is the Webb Optical Telescope Element Manager at NASA Goddard, once said that aligning the primary mirror segments as though they are a single large mirror means each mirror is aligned to 1/10,000, the thickness of a human hair. What's even more amazing is that the engineers and scientists working on the Webb telescope had to invent how to do this. The James Webb Space Telescope is primarily going to work in the range of infrared wavelengths. Infrared radiations are nothing but an object's signature in the form of heat. This means that every object at a non-zero temperature would emit some infrared radiation. So if Webb's primary mirror is kept at the same temperature as the Hubble's, then the faint infrared light from distant galaxies would get lost in between the infrared glow of the mirror itself. So, to get rid of this interference, Webb's mirror will be kept at around -220 degrees C, and to achieve this temperature, the James Webb Space Telescope is going to have a 5-layer sun shield that is the size of a tennis court and will eventually weaken up the heat from the sun by more than 1,000,000 times. In total, Webb's primary mirror is nearly 7 times the size of the Hubble's and many times more advanced and powerful than all the space telescopes launched so far. So with all of its advanced features, and especially its unique primary mirror, Webb will curate a new story of cosmic observations. Undoubtedly, the James Webb Space Telescope is about to bring a revolution. How deep will James Webb look? Between 240,000 and 380,000 years after the Big Bang, the universe cooled to about 30,000 K, approximating the sun's surface today. At this temperature, it was cold enough for electrons to combine with nuclei to form hydrogen atoms. As the free electrons were absorbed, the universe became transparent to light, that is photons. The photons that were released are what we see as the CMB today, and is the earliest we can observe. Known as the recombination/decoupling epoch, signifying absorption of electrons and release of photons. It was followed by dark ages, from 380,000 to 150 million years, about which we know very little, when the universe was dominated by mysterious dark matter. The emergence of the universe from dark ages into the reionization epoch, with gravity taking over, ushers in the formation of first stars and then galaxies between 200 to 500 million years after the Big Bang. With its infrared capabilities, the James Webb Telescope is expected to observe the nurseries of baby stars and evolution of galaxies in this period. In comparison, the Hubble telescope scanned stars and galaxies about 1 billion years after the Big Bang. However, enhanced resolution techniques in the Hubble Ultra Deep Field studies have enabled the Hubble to take images from 400 to 800 million years after the Big Bang. James Webb is expected to bring in more data of direct observations of the early universe, a clue to the correct value of the Hubble constant, and consequently to the question of new physics on the horizon of science. It will also observe formation of planetary systems and atmospheres of exoplanets in the near universe for signatures of life. Thus, James Webb has such broad capabilities that it will refine our picture of the cosmos from very early stages to the present. Although James Webb is known as successor to the Hubble telescope, it will also carry on from where the missions of Kepler and Planck telescopes left. Watch the birth of stars. The birthplaces of stars are full of dust. While they make for breathtaking photos, the dust blocks scientists from peering right into the heart of these clouds when they look at them with visible light. Luckily, infrared light from stars can penetrate through the dust to give scientists a whole new take on an old view. Red light can pass through the dust in the Earth's atmosphere better than the shorter wavelengths, the blue lights. Marcia Reeks said this, an infrared astronomer at University of Arizona, who is the principal investigator of one of Webb's infrared cameras. The same principle explains why infrared light can penetrate even further through dusty galaxies than visible light. If you look at the setting sun, it tends to look much redder than when you look at it in the daytime. It's the same thing. Hubble's limited infrared capabilities have barely scratched the surface for studying stellar formation. Webb's broader infrared range will enable scientists to peer deeper into the dust. Young stars emerge from the dustiest pockets, where it's most challenging to see through. Thanks to Webb's high infrared sensitivity and spectacular resolution, scientists might be able to sift through the dust to make out these infant stars with unprecedented detail. And Webb might help scientists figure out how the dust cooks up a star, why stars form in clusters, and how planets form around a star. Detect possible chemical signatures of life on other planets. If life exists outside of Earth, it will release distinct chemical signatures, such as by breathing carbon dioxide and photosynthesizing out oxygen that can transform a planet. Analyzing the chemicals in a planet's atmosphere will not only allow scientists to look for life, but also enable them to assess a planet's habitability. Webb can detect infrared wavelengths for fingerprinting chemicals, such as water and methane present in the atmosphere of exoplanets, which are planets beyond our solar system. Webb contains two instruments that will allow scientists to unravel the wavelengths of infrared signals from solar systems beyond ours, to unweave the colors of the infrared rainbow, so to speak. When an exoplanet photobombs a star that our telescopes are gazing at, the starlight will experience a dip in certain energies corresponding to the chemicals in the exoplanet's atmosphere. If Webb happens to be looking at the right star at the right time, it can chemically analyze the atmosphere of the star's planet by analyzing the blip in the starlight. However, humanity's understanding of these exoplanets has barely extended beyond the fact that they're there. It's challenging for current technology, such as Hubble or on-Earth infrared telescopes, to carry out infrared spectroscopy on new exoplanets of interest. Hubble works with a much narrower band of infrared energies compared to Webb. Ground observatories are shrouded in Earth's atmosphere, which itself is an absorber and scatterer of infrared light. The Earth also emits background infrared radiation that would overwhelm the faint signals coming from the deep cosmos. In space where Webb will be, Earth's atmosphere and warm radiating surface are out of the way for an unobstructed view of the night sky. That's all in this video. If you like the information, please hit like and subscribe to this channel. And be connected to this channel for more space information.